All right, every year, right around this time, the GCC Foundation offers a number of scholarships. The GCC Foundation pretty much exists to give students scholarships, and the only people eligible for these scholarships are GCC students. So that's something like 2,500 people, the vast majority of which are not going to apply for these scholarships. And so this might be the best opportunity you ever have in terms of odds at like free money. It's a very small pool of people applying for a significant pool of money. So if you go to just the GCC homepage, there's a big old link right here. It says Apply Now Scholarships. And so you click on that, while that's loading up, I'll show you just a couple of the scholarships. So this is a 9-page document with a listing of all of the scholarships. So for example, this first one right here is one scholarship worth $1,000. You can be full-time or part-time. Awards are made on the basis of scholarship, financial need, and character. And let's scroll down a little bit here. For example, this scholarship right here is one scholarship worth $650 given to a female student looking to pursue a higher degree. So not all of you are eligible for all of these awards here, but many of you are eligible for most of these awards here. And the nice thing is that the scholarship application is very simple. You fill in, I'll come over to this page. This document that I'm showing you is this PDF linked over here, the scholarship list. Deadline is March 1st. This tells you how to apply. You need to go to My GCC and you need to log in and you need to follow this path right here. And when you do that, it will take you right to the scholarship application. It is very bare bones basic. You just have to fill in a couple of very simple questions about yourself. And then you need to write a 250 to 500 word personal biographical statement. It is right here. And then regardless of how many of those scholarships you want to apply to, you just write that one essay. And the scholarships all appear there as a checklist. And you say, oh, I want to apply to this one, and 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 I'm done. And you can apply to like 50 scholarships with one application. If anybody doesn't mind sharing, has anybody won any of these scholarships in the past? Is the application process difficult or quick, or it's quick? Yeah. All right. So like I said, March 1st is the deadline. I would get on that if I were you. For some of them, that would exclude you from being eligible, but for some of them, you are eligible. So really, you just need to go through the list and read and figure out which ones you're eligible for. Other questions? All right, so throw your name in the hat. Okay, good morning, welcome back. Happy Monday. Today, February 6th. Quiz number 1 is due. Throw that in the folder right now. It is due at this exact moment. I take homework late. I take projects late. I will not take this quiz late. So in whatever state of completion it is in, you throw it in the folder right now. Project number 2 is officially assigned. Go ahead and grab one from your table. Anybody got one of those? Brand new projects. Project number 2 is going to be due on February 13, 1 week from today. You can write that on the top if you want. It is not written on that project. February 13th is the due date. Okay, and today we cover section 6.3, Introduction to Differential Equations. Questions on the calendar? Just while the calendar is up here, I'm going to scroll way down to the bottom. I will tell you that this is like a one-day, very quick intro to differential equations. We will also spend the last week of the semester talking about differential equations. Okay, so here we are with our daily summary. In this class, we solve differential equations and initial value problems, including problems related to motion. And I will say that this material will give us an opportunity to practice all of the brand new antiderivative formulas we created last class, but in a slightly different context. So it's really more of the same, lots of antiderivatives, but a different context. Number 1, a differential equation is an equation involving derivatives. A simple example, a satellite has a constant velocity of 80 meters per second. If we let s of t represent the position of the satellite at time t, then we can write ds dt equals 80. I'm hoping you buy that. because the derivative of position is known as velocity. And so all this is saying is that the velocity is 80. That's what it says. But it's written in calculus terms. It's written as a differential equation because it is an equation that involves a derivative. Okay, number 2. They can get much more. Oh, by the way, we can solve this, right? Let's just do that real quick. Who has a derivative equal to 80? 80x, in this case, not x, t. Right. So there you go. There's the solution to that differential equation. Tack on a plus c if you're feeling like it. But that's it. Right? That is a function whose derivative is 80. Okay, they can get much more complex. For example, y double prime minus y prime minus 12y equals 0. In your mind, you're imagining y equals some function with x's in it. And in English, what this says is that you are looking for some function with x's in it, where when you take the second derivative of that function, just imagine like x cubed, right? So you take the second derivative of x cubed and you get whatever you get. And then you subtract the first derivative of x cubed, and then you subtract 12 times the original function, 12 times the original x cubed, and maybe you get 0. Like always get 0 if everything just magically cancels out. If x cubed made it so that everything all canceled out and you got 0, then we would say x cubed is a solution to that differential equation, okay? Let's try a couple of things that aren't going to work, and then we'll find one that is, or I will share with you one that does. Okay, so I said x cubed. How about we'll just try like x to the 5th and just see what happens. So according to this differential equation, we need the second derivative and the first derivative. So let's get calculating. First derivative is 5x to the 4. Second derivative is 20x to the 3rd. And so if I take all of that and I plug it back into my original, it would say the second derivative, so that was our 20x to the 3rd, minus the y prime, 5x to the 4, minus 12 times x to the 5th, the original y. I'm going to put equals with a question mark here because I don't know yet, equals 0. Now, to say whether or not x to the 5th is actually a solution to that differential equation doesn't mean can you find an x that makes this equation true. It means this equation is supposed to be true for every x. And it most certainly is not, because the left-hand side didn't all vanish and become 0. Sure, there are values of x that make this equation true, but that's not what this is about. We're trying to find a function that makes this equation true all of the time for every x. So what that means is that x to the 5th is not a solution to the differential equation. Just didn't work. Okay. All right, so that one didn't work. I'm going to jump you to the punchline and give you one that is going to work. Let's try another one instead. Let's do e to the, think, negative 3x. Okay, I think this one's going to work. So y equals e to the negative 3x is a function that I'm pulling out of a hat. You don't need to worry about where it came from at this moment. But let's just see if we can figure out if it is a solution. So that means we got to get calculating, right? So y prime, go this way, y prime equals e to the negative 3x times negative 3. That's our chain rule. E to the stuff times the derivative of the stuff. And then y double prime. Yes, so it's going to be another negative 3 coming down. So it's going to make a 9. I'm going to write that as a 9. E to the stuff, right? Negative 3x. Okay, so we calculated both of our derivatives. And now we're going to plug them all into this original thing right here. So it says y double prime. What are we putting? What are we putting? 9e to the negative 3x. See it? Y double prime, just substituting in here. Minus, instead of y prime, what are we putting? Negative 3 e to the negative 3x. So there's a subtraction from the original equation, and then negative 3 was part of the derivative. And then finally it says minus 12y. What are we putting? Minus 12 e to the negative 3x. That's minus 12 of the original, okay? Equals with a question mark 0. That's what happens. It all cancels. And indeed, the left-hand side equals the right-hand side. Okay. So what's the big question you have on your minds right now? Where did the e to the negative 3x come from, right? Okay, there's an entire course involving solving differential equations. It is called Differential Equations. I have taken that course. You have not taken that course. You don't need to worry about where it came from right now. We will solve simpler differential equations today. This is not one of the ones that we will solve, but what I do need you to take away from this is that it is easy for you to check whether or not something handed to you is a solution. I handed you x to the fifth up in red. What was our conclusion? Not a solution. I handed you e to the negative 3x. What is our conclusion? Y equals e to the negative 3x is a solution. Okay. You can wonder where it came from. That's not a question we're going to answer today, but you do need to be able to verify or show that something is not a solution. Evan. Yeah, so we're going to do a motion modeling problem on the next page. I will say that this equation right here looks like it maybe is just kind of made up, but actually is quite, that's what a lot of spring type equations look like springs that I don't know all of the different forces associated with spring stuff anymore, but when you're analyzing motions of springs, and are they going to like oscillate like slower and slower or whatever, you get equations that look an awful lot like that one right there. Okay, let's move on down here. Okay, so our differential equations are all going to have this form right here. Dy dx equals some stuff involving x. So here's our first one that we're going to solve together. What's the solution of dy dx equals cosine of x minus 1? So in English, we are looking for a formula y equals some stuff with x in it, so that when you take the derivative of that formula, you just get cosine of x minus 1. Well, what we're after then is just an antiderivative of cosine of x minus 1, right? So let's find an antiderivative. Y equals antiderivative of cosine x, sine x. Is it positive sine x or negative sine x? It's positive, so just be careful with those signs. Negative x, where did that come from? Sorry, negative 1. Yes. Yes, it came from negative x. So that is one solution of the differential equation. We'll just check it in our heads here. In order to check this, we should take a derivative and plug it in, right? Well, when you take a derivative, what do you get? Cosine of x minus 1, which is exactly what the equation says. When you take the derivative, you should get cosine x minus 1. That is only one solution to that differential equation. How are the different solutions related? Just the plus c, right? So that is, if I just say a solution, you can pick your favorite c that you want, minus 18, whatever you want to do. But if we want the general solution, you got to tack that plus c on at the end. Okay, so all the differential equations we solved today are going to look like that. Derivative equals something with x's only. To get a specific solution, meaning like a specific value of that c, we need an extra condition, something called an initial condition. Oftentimes it's y of, some x value equals some y value, and the zeros are supposed to represent like that it's an initial value of some kind. For example, let's solve the differential equation, same one that we just saw, coupled with this initial condition that y of pi is equal to 1, just in case that notation isn't super familiar. It's just sort of treating the y like an f, like a function type thing, okay? So it's just saying f of pi is equal to 1. All right, so let's write our general solution from the previous page. We said it was y equals sine of x minus x, but then if we want to be general, we got to tack on our plus c. And the goal is to pick the particular value of c that makes y of pi equal to 1, okay? And so in order to do that, we're going to change the x's into what letter? Into what number? Into pi, and we're going to change the y into 1. That's all we're doing, okay? So change the x into pi, the y into 1, and that will give us enough to find c. So the y over here becomes 1 equals sine of, we said x becomes pi. This x also becomes pi, plus the c is the thing we're trying to find. Okay, 1 equals, without a calculator, we should know sine of pi is 0. 0 minus pi plus c. So what is c equal to? 1 plus pi, or pi plus 1. Oftentimes students stop right there. They say, oh, I found c, I'm finished. But technically, we were looking for a solution to the differential equation. And our solution is going to look like blue. Finding c is the second to last step, but rewriting blue is the last step. Yeah. That's our final answer there, okay? So when you got c, you're pretty much done, but make sure you write the actual solution as your last step. And this thing in the box satisfies two things. Number one, if you take its derivative, you will get exactly what the differential equation said. You will get cosine of x minus 1. And then all of this 1 plus pi stuff, when you take a derivative, vanishes, right? And then additionally, if you plug pi in for all of those x's, what will you get for y? You will get 1. So that thing in the box satisfies both the differential equation and the initial condition, okay? Okay, another vocabulary phrase here. This problem, a differential equation plus an extra condition that's highlighted, is called an initial value problem. Okay, so our last example is from physics. We know velocity is the derivative of what? Distance or position, right? Or height, I guess, sometimes. And then the other relationship here, well, what's the next one up the chain? Acceleration is the derivative of velocity. Okay, so let's give this a shot. Suppose a ball is thrown upwards from the edge of a cliff that is 100 meters above the ground. So changing that into our familiar initial condition notation, it's s of 0 equals 100, where s is our position or our height, okay? So initial height of the ball is 100 meters. And it's thrown upwards with an initial velocity of 74 meters per second. And again, that means that v of 0 equals 74. Initial velocity is 74. We're going to take gravity as negative 10. Negative 9.8 is closer, but we'll just call it negative 10 meters per second squared, which means that a of t equals negative 10 for all times t. Okay, a of t is a constant negative 10 acceleration due to gravity. So we're going to derive the formulas for the object's velocity and position at any time t. I actually don't like using this word derive here. I'm changing it to create. Derive is like a calculus thing. You can take derivatives. That's called deriving. We are doing calculus things here, but I don't want to mislead anybody with that word. We're going to create the formulas we need for velocity and position, and then we'll figure out how fast the object is moving when it hits the ground. Okay, so this is a very easy problem. If you happen to know a formula that you probably saw very early on in Physics 1 about position stuff. So I mean, there's a lot of physics formulas. So I'm going to write the one I want. You tell me if you know this formula. Is that something? Yes, that's something. Are these the same letters that you use? Yeah. Great. Okay. So Ted probably So Ted probably shared this formula with you. All right, I've known Ted for 8 years. I don't believe a word that man says. So we're going to cross this off or pretend we don't know anything, and we're just going to build this thing from scratch. That is a kind of complicated formula, right? I mean, like, yeah, it's true, but it just sort of appears out of no place. Well, not anymore. Today we're gonna prove that this formula is reasonable. Okay, so we start with that guy right there. A of t equals -10. We're gonna rewrite that in a different way. We said that acceleration was the derivative of what? Velocity. So how about I write dv dt equals -10, just changing acceleration to the derivative of velocity. That is what those symbols mean. Good. What is this thing called, this equation? It's the title of our lesson today. That is a differential equation, and we're going to solve that differential equation. So we're looking for someone whose derivative is -10. Whose derivative is -10? It's -10t. What's a good name for the, like, what letter are we saying is the solution here? Is v. We are saying the formula is that the velocity is -10t. That's the function whose derivative is -10. This is a specific one, but we want the most general one. So we tack on our plus c right there. Okay. Next step is to find the c. We have a specific velocity value given to us. I'll write it over here as a reminder. V of 0 was 74. Do I have that right? Okay, so we plug in, and we're going to find our c. So what does t become? 0. So this becomes -10 times 0 plus the c, which we don't know. What does v become? 74. So that means that c is 74. Which means that we rewrite this. Remember, don't stop when you have c. Rewrite your formula. So v equals what? -10t plus 74. Great. Okay. So we're going to pick that equation up, and I'm going to put it over here. But we are going to use the fact that velocity is the derivative of position. So instead of v, I'm going to put the s dt equals, and I'm copying the right-hand side, -10t plus 74. And what is that kind of equation called? That is a differential equation, and it is begging to be solved. So let's solve this differential equation. What's a good name for the letter that we put on the left-hand side? Yeah, the solution that we're about to find is s, right? It's s equals some formula with t's in it. Okay, -10t. This one is a little bit tougher. Well, let's give it a shot. We do have our basic power rule from last class, which says you add 1 to the power and divide by the new power, right? So that t becomes t squared over 2. But that -10 is a constant multiple. And what do we do with constant multiples? Copy them, right? It's imagining like there's an integral and that -10 was inside, and then you just pull it right outside. And so that's a -10 right there. Okay, plus 74 came from 74t. And then to make it general, plus c. It's not the same c as above, but I think it's okay to use the same letter c. Okay, let's find c. I think we had some specific info, right? What did we have? S of 0 was 100. Okay, so we give this a shot. Left-hand side becomes 100 equals, the t's become zeros. So -10 times 0 squared over 2 plus 74 times 0 plus c. So c is 100. And so then we'll put our final answer, I think it's this guy. S equals, oh, let's clean this up just a little bit. So negative 10 over 2 is negative 5 t squared plus 74t plus 100. So that right there is the formula for the position of this object at any moment in time. Now you remember, Ted told me one day that S was 1/2 AT squared plus V0t plus S0. So let's see, S0, that's supposed to stand for initial position. What is it? 100. Did the 100 end up popping out there at the end? It did. V0 stands for initial velocity. What was it? 74. It's supposed to be 74t. Did we get that? We did. This is always the tricky part for me. 1/2 AT squared. Like, I like the way it sounds. Like, I just like to say 1/2 AT squared, but it's just mysterious to me. But did we get it? What was A in this problem? Negative 10. What do we have in front of our t squared? Negative 5. And it's not a coincidence, right? I mean, like you saw the negative 10 getting divided by 2. That's the half right there. And so, in fact, in a lot of physics formulas, you see a 1/2 and then a something and a squared. That is almost certainly because we took an antiderivative of t, or whatever the variable is. That 1/2 and the something squared. What's the kinetic energy formula? 1/2 mv squared, right? I don't know how to derive the kinetic energy formula. Like, I know how to do this one, but I would put my money on that thing being an antiderivative. That 1/2 and that squared is just so typical of an antiderivative. Okay, so I think the last piece to this one was to use one or both of our formulas here. It says here, then we'll figure out how fast the object is moving when it hits the ground. Okay, let's give that a shot. How fast the object is moving when it hits the ground. So here's the how fast formula. That's our velocity. And then the other formula we built was the position. So the how fast is going to be answered by this. So if I can plug in a certain time, I'll know exactly how fast the object is moving. But the difficulty is that we don't know when the object hits the ground at this moment, right? So as soon as I find the right time, I can plug it right in there, and that gets me the how fast. So how do I use this formula to figure out when the object hits the ground? 0 for the S, right? Because when the object hits the ground, its height above the ground is 0 meters. So 0 for S. Ground. S equals 0. So let's give it a shot. 0 equals negative 5t squared plus 74t plus 100. And how do we solve that equation? Wolfram alpha is the right answer, actually. Yeah. All right. Wolfram alpha. So I mean, it's just a quadratic equation, right? So I mean, if it factors, then go for it. It almost certainly does not factor, which means you could do the quadratic formula, or you can do Wolfram alpha. All right. So if you haven't used this site, shame on you. It's fantastic. You just type in the equation you want. 0 equals negative 5t squared plus 74t plus 100. Hit enter. And we got lots of information. So the graph of y equals that thing is this parabola looking guy. Looks like there's a 0 out here at around 16 and another one over here at negative 1.2, which is irrelevant for us in this problem. They've written our equation in a couple of different forms just to show off. And there's the exact solutions with radicals, which reminds us a lot of the quadratic formula, right? That's the kind of thing we'd expect. And then a couple of points here on the number line. So 16.046. Just got that written down. 16.046. Okay. So this tells us t equals 16.046 plus a t that's negative, which is irrelevant. This tells me how long it takes for the object to hit the ground, 16 seconds. I want to know how fast it's going. So what am I doing with this 16? Plug it into the velocity formula up above. Okay, so we had v equals 74 t, no, v equals, what was it? Negative 10, thank you. Negative 10t plus 74. And so negative 10 times this t that we just found right here. Plus 74. Somebody give me a number here. Okay, that's our velocity. It's that many meters per second. This 16 was seconds. Good. All right, so in terms of like test questions, I really like this question. I just do. I think it pulls together so many different things that we've been working on, and also is something that's applicable. I think it is complicated, but not overly so. Like I think it's like manageable, but pushes us a little bit. I really like this kind of question. So you should practice this kind of question. Okay, I think that is good there. If we've got everything here, and the activity starts on the next page. There's a reference to a graphing utility. If you don't have one, you can just skip that question. That's not the most important thing. Let's see how far we can get.